Hello everyone. In this video we'll design channels. The first problem we'll look at is a best hydraulic section problem. In this problem the channel is lined, meaning we're not worried about the channel bottom or the channel sides eroding. So in such a case we would like to maximize the flow for a given area. In the second problem, it is going to be an unlined channel, meaning depending on the material that makes up the channel, beyond a certain threshold of velocity or force, the channel starts eroding. In such a channel, then the threshold velocity or the threshold force is going to be the driver. So let's start with the first problem here. We are given, so it's a rectangular channel, we are given Manning's roughness, we are given the design discharge, we are also given the channel slope. Using this design criteria, we would like to design the best hydraulic rectangular channel. And at the end we'll also estimate the freeboard height for this channel. Freeboard height is the height above, so if you take a look at this figure, the height above the water surface to the bank is the freeboard height, and we would like our channels to have freeboard height because during disturbances to the water surface, we'd like to make sure the water is contained within the channel banks so it doesn't flow out of the or over the channel bank. We can directly start from the relationship for best hydraulic rectangular channel, where so for best hydraulic rectangular channel, the channel width is twice the water height. But let me just step back and show you how we get this. For best hydraulic channels of any shape, we are trying to maximize the flow for any given area. So to do that, we would like to minimize wetted perimeter. Wetted perimeter is what resists the flow. So if we can minimize the wetted perimeter, we can maximize the flow through the same cross-sectional area. So we can express that in terms of this derivative, dp over dy equals 0 for the best hydraulic section. In this case in particular, we're looking at rectangular channel, so perimeter equals b plus 2y. So this then can be expressed as d over dy b plus 2y equals 0. B, then using area, so we're looking at a constant area, so area equals b times y. That gives b equals area divided by y. Area is a constant in this case, so we can take that out. Area times d over dy 1 over y, plus the second part here, 2 times d over dy y equals 0. So this gives us a So -1 comes from the derivative, and we are left with 1 over y squared in denominator plus 2 equals 0. Now we can plug back our area. Area is b times y. So it's minus here. So let's take it on the other side. So it's positive. by over y squared equals 2. Y cancels one of the y in the denominator, and that gives you b equals 2y. So you can do the same for any other hydraulic or any other channel shape. So starting with b equals 2y, then we can apply Manning's equation to calculate the hydraulic radius. So using Manning's equation, Q equals 1 over n A times hydraulic radius to the power 3, hydraulic radius to the power 2 over 3 times slope of the channel bed to the power half. So in this case we are given Q, we know Manning's roughness. A can be expressed as hydraulic radius can be expressed as area over perimeter, and we are given S naught. So let's express it in that form first. 1 over n area to the power 5 over 3 over perimeter to the power 2 over 3 S naught 1 over 2. Okay, so it's a best hydraulic channel. So the area can be expressed as by, where b equals 2y times y, so area is going to be 2y squared. Similarly, perimeter is b plus 2y, but in this case b equals 2y, so our perimeter in this case is going to be 4y. We are given a Q of 25. Let me make sure the units are correct. Okay, 25 meter cube per second equals, we have a roughness of 0.035. Area is 2y squared to the power 5 over 3. Perimeter is 4y to the power then of 2 over 3, and the last term here, which is the slope, let's actually write that down. We have a slope of 0.003 to the power half. So now we have an equation where the only unknown is y. We can then solve for y. We'll get a y value of 2.59 meters. The channel width then can be calculated. So b equals 2y. So plugging in the value of y, we get b of 5.18 meters. So that equals B. So we have a design for the base hydraulic rectangular channel, but we want to make sure the flow isn't supercritical. If the flow is supercritical, then at some point along the channel, the flow can go into a subcritical flow. So there will be hydraulic jump followed by the water depth increasing. So if something like that happens, then the water can flow over the bank. So we need to make sure the flow is subcritical. So let's check the Reynolds number. So let's start first with velocity. Velocity is Q over area. We have discharge of 25 meter cube per second, and we have area of by, so 2y squared 2 times y of 2.59 meter squared. So this gives us a velocity of 1.86 meter per second. Then we can calculate Reynolds number. The Froude number. I think I earlier said Reynolds number. It should be Froude number. Froude number is velocity divided by g, square root of gy. That equals 1.86 meter per second divided by square root of 9.81 meter per second squared times the width, the channel depth 2.59. So this is not channel depth, the water depth, and that gives us a Reynolds number of 0.369. This is less than 1. It's subcritical flow, so we're not worried about a hydraulic jump occurring and the water height increasing. So our estimate of y and b is good. So now we would like to estimate the freeboard height. So this is a figure from your book, figure 6.15. It's a figure from Bureau of Reclamation. There are different ways. There's not one way to estimate this, but a figure like this is one way to estimate the freeboard height. So in our case, the figure is in units, in British units, so let's convert our Q into British units. So let's use the factors. So for okay, 0.348. In 1 meter cube per second, you have 0.348 cubic feet per second. It's 0.3048. Actually, it's the other way around here. Okay, so once we use the conversion, we'll get Q of 883 cubic feet per second And using this key value, we can estimate the freeboard height from this figure. 883. So using my virtual ruler here, so this is 600, that's 800. Okay, so somewhere here, since this is a logarithmic scale, towards the middle is close to our value of 883. So for that Q, we'll get a freeboard height of about 3.4. So freeboard height is equal to 3.4. Let's just stick to our estimate that 3.4 feet, and this is going to be close to a meter here. So I'll just call it 1 meter. It's close to 1 meter. So in our design of the channel then, we can just go back up here. We have a Y value of 2.59, and we want a meter of all that. So the total height is going to be 3.59, and the channel width here, B, is going to be 5.18 meter. So that's our design for this channel. In the next problem, we're looking at the unlined channel. The material of the ground where the excavation is done to form the channel is silt clay soil. So depending on the material, there is a maximum velocity that the material can hold before erosion starts taking place. So table 6.7 provides the maximum permissible velocity for different types of channel material. So in our case it's silt clay. We're looking at units of SI. So we have maximum velocity of 1 meter per second. So velocity max for the channel is going to be 1 meter per second. Okay. Okay. So we are given all the channel properties here. This is a trapezoidal channel. The side slope is 3. We're given the Manning's roughness, the design discharge, and the channel slope. So using Manning's equation, let's use the velocity form of Manning's equation. V equals 1 over n times hydraulic radius to the power 2 over 3 times square root of the channel bed slope. So here we now know the velocity, which is going to be our velocity max. That's the threshold we know the Manning's roughness, we know the channel bed slope. So from this we can plug in all these values and calculate our hydraulic radius. So from this one we'll get a hydraulic radius of 0.393 meters. So let me just expand that here. V times N over S naught 1 over 2 to the power 3 over 2. So at this point we'll just plug in the numbers. Once we have hydraulic radius, so the next step we can use the definition of hydraulic radius, which is A over P. The cross-sectional area can further be expressed as Q over velocity. So we have Q of 4.58 meter cube per second divided by velocity of 1 meter per second divided by P, so plugging in the value of hydraulic radius that we just calculated, we can then express P as 4.58 meter squared divided by 0.393 meters, and that'll give us perimeter value of 11.65 meters. Before we get into part 3, let's expand the weighted perimeter in terms of channel width and depth. So P then can be expressed here as B plus 2 times y times 1 plus m squared. M we're given is 3, so we can then write that as B plus 2 square root 10 times y equals 11.65. We'll just skip the units for now. That'll give us B equals 11.65 minus 2 root 10 times y. Now we can move into the cross-sectional area expression. Cross-sectional area is 4.58 equals B y. So we can just express B in terms of y using the previous equation. 11.65 minus 2 square root 10 y let me just add the y's in here, plus m is 3 y squared. So what we ended up getting is an equation in terms of y alone. So 11.65 y minus, let me do plus 3 minus 2 square root 10 y squared equals 4.58. We can then solve this equation to get solution for y. There are two possible solutions. So the first possibility here is 0.45 meters, and the second solution you'll get is 3.05 meters. Now, using a y of 0.45 and the equation up here that relates b to y, we can get b of 8.8 meters, and using a y value of 3.05 we'll get a b value of negative 7.6 meter. So negative width, that is not a real width we can use, so this is impossible value for us to use. So we'll pick our y value of 0.45 and channel width of 8.8 meters. So the next step we'd like to do is to make sure the flow is subcritical flow, and the reasoning is, again, we do not want the flow to go through hydraulic jump and into a higher subcritical flow condition where the depth is higher. And if we designed it such that the flow is originally supercritical and the bank heights are enough, but after hydraulic jump occurs, the water depth is going to be higher and it might flow over the banks. So using Froude number equation, v over square root g d. So the difference here is, since this is not a rectangular channel, we want to use hydraulic depth instead of the actual water depth. So to calculate hydraulic depth, we start with the definition. Cross-sectional area divided by the top width of the channel is your hydraulic depth. So cross-sectional area we've already calculated, 4.58 meters squared, divided by the top width is bottom width, which is 8.8 meters, plus 2 times the side slope, which is 3, times the channel, the water height, which is 0.45 meters. So this will give us a hydraulic depth of, I'll just simplify it further, 4.58 meters squared divided by 11.5 meters, and this gives a hydraulic depth of 0.398 meters. So then we can go back to our Froude number equation. So velocity is 9.81 for acceleration due to gravity, times 0.398 for a hydraulic depth. This will give us a Froude number of 0.51. This is less than 1, so our design is okay. So in this problem, it's not asking us to find the freeboard, so we'll just limit our solution to the water water surface only. So Our final design then comes out to be y of 0.45 meters and b of 8.8 meters. So that's it for today. I'll see you in our next meeting. Thank you.